Hello and welcome to LeChateliers Principle Part 2. LeChateliers Principle Part 2 is going to feature changes in pressure and volume and how they affect a system at equilibrium. What is important to keep in mind about pressure and volume changes is they only affect gases. I like to say nothing but a G thing or a gas thing. A little throwback to some early rap I hope some of you guys know about. So when we talk about changing pressure only affects gases. Okay, and I'll show you how you figure this out. At high pressure, so when things are kind of like shoved together, we want fewer moles. Whereas at low pressure, we're able to have more moles of gas. So what will happen to a system, the system up here, when pressure is increased on this reaction? So what we have to do in order to assess this is we look at the reaction itself and we determine how many moles of gas are on either side. So in front of this, there's an invisible 1. There's a G here, so that's a gas. There's a 3 here, and that's a G, so that's a gas. So on our left-hand side, we have 4 total moles of gases. This is a gas also. We have 2 moles of gas over here. So we have 2 total moles on the other side. So when we increase pressure in this reaction, we are going to favor a shift to the side with fewer moles. In this case, that's going to favor a shift toward our 2 mole side. So we can call this shifting to the right, or also favoring the forward reaction. As this occurs, what we're going to do is we're favoring the production of NH3. So that will increase in concentration, and we are going to decrease our concentrations of N2 and H2. On the other hand, when we decrease pressure on this reaction, it's like we allow things to spread back out. So we don't need things all shoved together in only 2 moles. We're able to have 4 moles to take up that space. Gases like to, spread out as much as they can. So if we decrease our pressure on this system, we're going to favor going in the reverse direction. So we're going to shift to the left. We are going to favor our reverse reaction. And when we do this, we're now favoring stuff that's on the left, which is N2 and H2. So we're going to have an increase in N2 and an increase in H2. And we're going to have a decrease in NH3. So just to give you a little bit of a visual on what this looks like and why there are different moles on either side. So in our reaction here, our blue is representing nitrogen. So we're starting with 1 mole of nitrogen gas and 3 moles of hydrogen gas. So as you can see, this is 1, 2, 3, 4 different groupings of atoms. So that's our 4 moles of gas that we're talking about over here. When we rearrange these and stick them together differently, so the nitrogens break apart and 3 hydrogens get stuck on each of them. So you'll notice we take the same amount of stuff. In both cases, we have 2 atoms of nitrogen. Okay, so there's 2 blues on either side. There's 6 atoms of hydrogen or 6 greens on either side. But we have rearranged these in only 2 moles of NH3. So on this side, we only have 2 moles. We have all the same stuff. They're just rearranged differently. If you were to move to New York City from your house here in Marcellus, you would have to rearrange your stuff in your new tiny city apartment to get it to fit better. That's what's going on here. So when we're at very, very high pressure, it's like things get shoved together. When we're at very, very low pressure, things are able to spread apart. If you have a large house, you would let your stuff spread out all around it. You're not going to just shove everything into one room. So when we're at high pressure, we favor an arrangement that takes up less space or has less moles. When we're at low pressure, we allow those moles to spread back out. There's a way you can draw this to help you remember. So if you look at either side, you got to make sure you're only counting moles of gases. So we have 1 mole of a gas here, 3 moles of a gas here. So we have 4 total moles over here. This is a gas here, 2 moles over here. So to help us kind of keep in mind that our 4 mole side occupies more room, we draw a big old thing like that over here. And then what you can imagine doing is if this were a huge balloon, if you were squeezing it because you're at high pressure, you're going to go to the smaller side, or 2 moles. If you let that release, you let go of that balloon, you stop squeezing it, stop putting pressure on it, it would spread out like those 4 moles. Now, volume relates to this as well. We have to think about how volume is going to affect pressure. If we increase volume, so we let our gases have a bigger space, if we increase volume, we actually decrease pressure. So in decreasing pressure, keep in mind we have our 4 moles of gas over here. We have our 2 moles of gas over here. So if the volume of the reaction vessel is increased, we're able to let everything spread out because that pressure is decreasing. So we're going to shift to the left. In other words, we're favoring the reverse reaction. And we're going to have an increase in N2. We're going to have an increase in H2. And we're going to have a decrease in NH3. So if you think about that picture we drew on the other screen, when we're talking about bigger volume, we are favoring this side over here where we have lower pressure and we can let things spread out. If we were going to decrease volume, so we make our reaction vessel smaller, decreasing volume will increase pressure. If the volume on the reaction vessel is decreased, it's like we're shoving everything together, so we have to go to that side with less moles. So we are now going to shift to the right. In other words, favoring our forward reaction. And as we do that, we're going to have a decrease in our concentration of N2. We're going to have a decrease in our concentration of H2 because we're favoring NH3. NH3 takes up less moles of space and therefore is favored when we have very little space or high pressure.